I made a whole presentation to do this because I thought there was going to be more of not technical people. You all here know already what we are doing, but I think it's okay. I will pass all the presentation and then I'm going to give a quick demo, okay? Let me share my screen here. Can you see?
Yep.
Okay, so this is just an enhanced version of the presentation that I did, I think, 2 or 3 months ago. And I think that I will use this presentation in other meetings also to present the idea. And uh, you will see how it goes. Okay. So what we thought about for the people here also who don't know what we were working, we are working on this LSDB server with a server application idea for some months now, and I'm going to talk a little bit about this. So I'm Gustavo. I work on S Plus, the Southern Photometric Local Universe Survey, and I work on the server side since the data reduction, all the infrastructure with the virtual machines in the server, to the data distribution. So the data distribution happens on S Plus Cloud that we are very proud of it. So why I think that the first we need to start from our motivation. So why LSTB with a server application? And I need to make a disclaimer that all of this is from my experience here in the S Plus collaboration in South America, that students usually don't have good computers or don't have sufficient power, processing power, low RAM, and especially storage. So of course, we have storage and good computers on the universities, but at least for me, I think it's always best to do science on our own computers. And I gave an example here that Gaia DR3, the source catalog has 700 gigabytes. And to generate the hipscat for this in the local storage, we'll need at least 1.5 terabytes because 700 for the source and more 700 for the hipscat generated. But of course, after it's done, it's the dream because LSTB, it's almost magic how it works. So our idea here was why not bring LSTB to everyone generating the hipscat on the server side. And at first, this is nothing new because you could already point LSDB to a server before, just how you are seeing here. So you could generate it on the server side and use a proxy to point it and read just as it is here. And you can see that it still performs much better than the tap. But an important thing to mention here is that these tests were made on S plus DR4, and DR4 has 380 columns. And when you are querying through a remote a HTTP file system, you cannot you lose the laziness of reading Parquet files. So, for example, you cannot read only the array and deck columns. And why would usually people don't want all the 380 columns? Usually they want, for example, ID, the coordinates, and the magnitude. So 20 columns maybe. So this is where our idea came from. It's to make the lazy part on the server side. So we point, you can see in this snippet of code here that we can point to a remote file system and then specify columns, certain columns and filters. And this is already working on the last version of LSDB. And LSDB will put, when it detects that it's a remote file system, it will put the parameters on top of the request. So for example, the columns that the user specified and the filters also. And then on the server side, there will be Nginx or a proxy of your choice that still points to the folder if there aren't any parameters. But if there are parameters, it will point to our server that does the lazy part on the server side. Here I did a quick benchmark of this also, of this exact query here. I put this for dots here because I selected other 20 columns. And you can see that we are getting closer to LSDB local. It's still not the same thing. but we are doing much better than the TAP anyway. So this is, I think, the important thing. So this server, it's written in Rust. It's almost the same as I showed in the last presentation. We wrote all the server, but the idea is the same. So it, as I said, it does the lazy load for the users on the server side. It returns only the necessary bytes. So for example, the bytes for the column specified. And also it is very lightweight because we know this because we did a stress test with almost 200 clients at the same time, and it performed very well. So here I have other benchmarks for now for a 10-degree cone search with 20 columns. You can see that nothing comes close to LSDB local. I think that the part that takes the most time is transferring the data to the network, but there's nothing we can do about this. So actually, we can refine the query. So for example, if we do refine the query, here it's RMAG below 20, we are getting closer to a good result here comparing to LSDB local. Having in mind that we are generating, we are not using the storage to the hipscat are on the server. So now the part that I wanted to talk most about is that we are doing now our releases in S Plus with in the LSDB way because it's much faster than the TAP, and I think this is the natural way of the science things should go. So we have DR4, all DR4 catalogs available in the LSDB way. I'm going to say LSDB way, okay? And all the value-added catalogs also, so they are partitioned on the server side, and we have a quick documentation on how to use this. This documentation, it's not complete, but I will make it complete soon. And also another cool thing that I wanted to show is that we are making IDR5 also available on the LSDB. And the I means internal, so it's protected data that only users from the collaboration should have access. And this is possible passing a authorization token through the storage options, just like you can see here. So we read the hipscat the same way as we would read the normal hipscat, but we always pass, for example, what we are using in S Plus is a JWT token with the authorization to the server. And this IDR5 link here, that it's the remote link, it doesn't point directly to a Nginx folder. So it points to a server that will authenticate the user, check the permission, and then it will redirect to internal folder of Nginx. So I'm going to show this in the notebook now. Okay, so let me share the other screen. Just a second. Just to show that all of this works. Okay, can you see the new one? Okay. So here I'm importing LSDB, of course, S plus data, that it's our S plus package. And I'm going to show why. Let me see. So I already ran this. Here we have in S plus data a function that will communicate with the server and will get all the available hipscat generated. So for example, if I run this, you can see that we have a lot of catalogs already. So all the DR4 main catalogs, so single and dual photometry, and we have a lot of value-added catalogs. And if you want, so this here just shows the catalogs available. And then if we want to get the link, because it's the link that we need, we would do something like this. So we would search for DR4 dual photometry, for example, that has the photometry on all 12 S plus bands. Let me run this here. And it returns the link for the main catalog and also the link for the margin. So 2 arcsecond margin. And if I go to the, if I copy the link and paste to a browser, it will be the normal Nginx folder. I don't need to show this now. Okay, so if we read this link, it's just as a normal hipscat partition as expected. But now we know that, I know that behind this link here, also in the server, we have our LSDB server application working. So if I search through this remote link here, and I put the columns and filters as I showed, it will work. It will do the filter for us. And I find this to work very well. I like very much to run this because it is very fast. We cannot run this fast using tab. So you can see here, I did a box search, for example, and it returns only the columns that I specified. And for example, I filtered for R auto below 18, and here we have only R auto below 18. So here I do other cone search, a bigger cone search now of 10 degrees. And here it is. And now the second part that I wanted to show, it's the internal data. So here in the S Plus package, we have a way to authenticate with this server. So I can input my credentials. And what this will return, it's the token. So this object now contains the token that we have. And we can simply pass this token to access the internal data, as I showed in the presentation. So here in the same function that got all the options here for the hipscat generated catalogs that we have available, if I pass the headers, it will show the internal that we have available, so only the protected ones. If, of course, if my user has the authorizations. So I can do the same thing as I did with the public. So I will get the links for RDR5 Duo, and I can get links here. And in this case, if I copied this link and paste it to a browser, it would not show the Nginx folder because, as I said, this link is pointing to the server that will authenticate first. And then it will show if the headers contain a valid token of a user with permissions, it will point to the Nginx folder. But otherwise, it will just fail. And I'm going to show working and failing. Okay. So here it's just with the DR4, but now IDR5 links. And I need always to pass the headers to get the internal data. So I will show this working, and I will show this failing also. So it ran. And now if I want to do a cone search, I have here, so IDR5. IDR5 data with the columns that I asked for. And then if I would like to, for example, if I have the link, if I'm a user that don't have permission, but I know this link, if I try to read the hipscat on this link without the storage options, it would fail because it would give a file not found error, because actually this only points to the server and not through a folder. So that's all. That's all I had to show. This was what I was working on this. Thank you.
It's impressive. It's like that. Yeah.
Thank you. I like this very much because it actually makes we only use step still because step is a convention. Because otherwise it doesn't make much sense to use step. In my opinion, of course.
Yeah, that's pretty good. I have a couple questions. I just wondering, you said that you add a filter, the performance is better. Like, does that mean you add more filters in your query for the cone search? The execution time will be better?
Yes, because the part that takes the most time, it's the let me just start my camera here. I'm sorry. So the part that takes most time, it's the network transferring. So if you put more filters, that means that probably you will get less objects, and then it will get faster.
Another thing is you mentioned about in your benchmark testing, you have like a 200 concurrent. Is it all cone search query?
Yeah.
With the different parameters or like I just wondering like what's the distribution of those
Yeah. So we
like
have
the radius, like the range of the radius you are using.
Mhm. So we had 200 clients at the same time with distributed coordinates. So I think that we did all with uh, 1 degree,
Is all 1 degree for the radius?
all 1 degree, but every time that the client finished the query, it would start another one. So we would always maintain 200 requisitions at the same time.
Okay. Yeah, that's the one thing. Maybe I have stupid question. I know the data you have all the data is in the cloud, right? The Parquet data.
Yeah.
And your server is also running in the cloud.
Oh, I'm sorry. It's not running in the cloud. We have a physical server here in São
Local
Paulo.
on-prem.
Yeah. We started with server in the cloud, but it started to get very expensive.
So
Then
okay. Your server is a cluster or is
yeah, we actually have two clusters here. One at Universidade de São Paulo, another at another university near São Paulo.
okay. I just wondering how big the clusters or the system specification allow you to run like a 200 concurrent cone search.
I could give you the specification because actually I ran in a virtual machine that had 24 cores, 48 gigabytes of RAM. So it's not actually
They're not very powerful.
yeah, not very powerful machine.
Okay. Okay, thank you.
You're welcome.
Just to make it clear, do I understand correctly that LSDB server doesn't do cone search itself, right? So it's LSDB doing selection of tiles which are needed, and then fine filtering on client side.
Yeah, right. This is a plan for the future.
Yeah. I'm just to make it clear that server is not doing cone search, but it's doing filtering of columns and column value and values.
Yeah, you're right.
That's just using like Parquet, things that are all native to Parquet itself and not having to do any additional work on top, which is pretty great too.
Yeah. No, it's
Yeah.
great.
Yeah, I'm interested to see like different radius performance, like what's the biggest radius you can process, how many, like for example, you have like a 5-degree radius and
Oh, actually, I showed a slide here with a 10-degree radius. And that we're not the stress test with 200 clients at once, but it is a comparison. Let me show here.
this is all Gaia data, is that right?
No, all these benchmarks that I did was with S plus data.
Oh, okay, sorry.
We are planning on putting other surveys here also, because then we could do the cross match also with this S plus with other surveys. So here, this is 10-degree cone search, for example.
Oh, right. For 10-degree cone search, how many concurrent process?
You mean local processes? So 10-degree
Server you are running.
with 10 workers at the same time.
Okay.
Let me see. The other ones that I showed here were 1-degree cone search that I showed. Yeah. Okay.
Thank you for answering my question.
You're welcome. Thank you for the questions.
Yeah, thank you for all the work too. This is so cool.
Yeah, I like to work with this. Thank you for having me here.